Welcome back. This is section 7.7. We're going to be doing more probability. We're going to talk about events with and, probability with and. We're also going to talk about conditional probabilities. So let's look at the objectives. We're going to find the probability of one event and a second event occurring. And we're also going to compute conditional probabilities. Here we go. So we first need to understand the notion of independent events. So two events are independent events if the occurrence of either of them has no effect on the probability of the other. And when we have the probability of independent events, so if we have two events A and B that are independent, let's read it that way. If A and B are independent, if A and B are independent events, then the probability of both A and B happening is the probability of A times the probability of B. So what we call the multiplication principle. So if A and B are independent events, I can do the probability of A and B both happening is the probability of A times the probability of B. So we multiply. So let's do some examples. Example 2. Not sure where example 1 went. Example 2, independent events in a family. So if two or more events are independent, we can find the probability of them all occurring by multiplying their probabilities. That's what we just talked about in the last slide, right? So we can extend it to the probability of A and B and C, is what we're saying. So if I want to know the probability that there are 9 girls in a row, probability of 9 girls in a row, assuming that the probability of a baby girl is a half, probability of 9 girls in a row would be 1/2 times 1/2 times 1/2. We're going to do that 9 times. So what we have is 1/2 to the 9th power, or if we do 1/2 to the 9th power, that's 1 to the 9th over 2 to the 9th. It's just 1 times 1 times 1. We could do it that way, right? We can multiply a lot of 1s up here in this numerator, so we get 1 over 2 to the 9th power, or 1 over 512. And if we need a decimal for that, we grab our calculator, we do 1 divided by 512, and we get 0.00195. 0.00195. We all carried out that far. So that is approximately 0.00195. All right, let's look at the next example. Example 3. Hurricanes. So the probability that South Florida will be hit by a hurricane in any single year is 5 out of 19. Question is, what is the probability that South Florida will be hit by a hurricane in 3 consecutive years? So 3 years in a row with a hurricane. So these are going to be independent events. Probability of a hurricane one year doesn't affect the probability of a hurricane in the next year. So we're going to do the probability of a hurricane times the probability of a hurricane times the probability of a hurricane. So 3 years in a row. So that's going to be 5 over 19 times another 5 over 19 times another 5 over 19. Which, if we do that calculation, that's going to be 5 times 5 times 5. We can grab our calculator. It's 125. And then 19 to the third power. Let's do 19 to the third power is 2,859. 2,859. And then if we want to do that as a decimal, we could just divide 125 by 6,859. And we come up with approximately 0.018. We'll just round it to 3 decimal places. Just pay attention to the directions on the assignments. They will tell you how they want you to round usually, or if they want you to leave it as a fraction, they will tell you that. Okay, let's go to the next example. More hurricane problems. Hurricane, more hurricanes. So if the probability that South Florida will be hit by a hurricane in any single year is 5/19, we're going to ask this question right here. What is the probability that South Florida will not be hit by a hurricane in the next 10 years? So that would be 10 years in a row with no hurricane. So what I'm going to do is find the probability of no hurricane by taking 1 minus the probability of a hurricane, right? Remember that from last time? Probability of no hurricane is 1 minus probability of a hurricane. So that's going to be 19 over 19 minus 5 over 19. So that would be 14 over 19, right? So the probability of not being hit by a hurricane in a single year is 14 out of 19. Probability of not being hit by a hurricane 10 years in a row is going to be 14 out of 19 to the 10th power. And then we will grab our calculator, and I think we'll just do this one as a decimal. So we're going to do 14 divided by 19. Oops, I missed a 4. 14 divided by 19. And we're going to raise that to the 10th power. That is going to be 0.047. 0.047. We'll just round it there. So that is approximately 0.047. And there's our answer. Okay, let's move on to the next slide. We're going to talk about probabilities with dependent events. So, two events are dependent if the occurrence of one of them has an effect on the probability of the other. That would be things like if I draw a card out of my standard 52 card deck, and I don't put the card back before I draw another one. The probability of a king on the second draw changes because I haven't put the first card back. So what we do is we have a formula that says if A and B are dependent events, probability of A and B is the probability of A times the probability of B, given that A has occurred. All right, so let's use that formula in a couple of examples. So example 4. You have won a free trip to Madrid. Oh, Spain. Yes, here we come. And can take 2 people with you, all expenses paid. The bad news, 10 of your cousins have appeared out of nowhere and are begging you to take them along with you. You write each cousin's name on a card, place the cards in a hat, and select one name. Then you select a second name without replacing the first card. So you didn't replace the first card, so those become dependent events. Your second draw depends on what happens when the first. If 3 of your 10 cousins speak Spanish, find the probability of selecting 2 Spanish-speaking cousins. We're taking 2 people with us, right? So the probability that they both speak Spanish is going to be probability that the first one speaks Spanish times the probability that the second one speaks Spanish, given that the first one was a Spanish-speaking cousin. So that's going to be, so that first probability, and they drew us a line here to remind us to write as a fraction. How many of my 10 cousins? 3 out of 10. So the probability that my first draw is a Spanish-speaking cousin would be 3 out of 10. But the probability that my second draw is a Spanish-speaking cousin is now 2 out of 9 because I still have 2 Spanish-speaking cousins out of the 9 remaining cards. Multiply that together, we get 6 out of 90, which we could reduce to 1 over 15 if we needed it as a reduced fraction. We can divide out of 6. But if I need a decimal, I'll just do 6 divided by 90, and that comes out to 0.067. We'll just round it to 3 decimal places. And you could use the calculator to reduce the fraction as well if you just needed a reduced fraction. Okay, let's look at example 5. Probability with 3 dependent events. So we can extend this idea to 3 events. 3 people are selected randomly, 1 person at a time, from 5 freshmen, 2 sophomores, and 9 juniors. Says that's 11 people total. Find the probability that the first 2 people selected are freshmen and the third is a junior. So we want the probability that the first one is a freshman times the probability that we chose a second freshman, given that we chose a freshman first, times the probability that we selected a junior, given that the first two were freshmen. So that first probability of freshmen is 5 out of 11 because we have 5 freshmen out of the 11 total students. Okay, then we multiply that with the probability that we chose a second freshman, given that the first one's a freshman. So that's now 4 freshmen out of the 10 remaining people. And then we multiply by the probability that we have a junior, given that we've chosen 2 freshmen. So we've only got 9 of the original 11 people left. So this denominator is a 9, but we have 4 juniors. So we have 4 out of 9. And then they went ahead and did that calculation for us. They multiplied it out and reduced it even. It reduces to 8 over 99. So you just multiply them together. 4 times 5 is 20 times another 4 is 80. So we have 80 out of, or I could just do this. 5 goes into 10, leaves a 2, right? 80 out of 990. Cancel the zeros, we get 8 out of 99. So different ways you can reduce the fraction. You could even use the calculator. Okay, let's move on. Okay, we're going to talk about the notation for conditional probability. So we have conditional probability. Probability of an event B, assuming that event A has already occurred. Let me try that again. Probability of event B happening, assuming that event A has already occurred, is called the conditional probability of B given A. And we write that with this notation. We read it, the probability of B given A, or the probability of B given that A has happened. Probability of B given A. All right, so let's do a couple of examples with that. So example 6, a letter is randomly selected from the letters of the English alphabet. Find the probability of selecting a vowel given that the outcome is a letter that precedes H. So think about your letters. We're looking for the probability of a vowel given that the letter precedes H. So this is the probability of a vowel if the sample space is restricted. So this conditional probability, you're really restricting your sample space. Probability of a vowel given that the letter precedes H. So our sample space, or the total possible outcomes, is right here. That is 7. And 2 of those are vowels. So my probability is going to be 2 out of 7. Probability of selecting a vowel that precedes H is 2 out of 7. And if we needed a decimal for that, we just do 2 divided by 7. And we get that is approximately 0.286. Okay. A couple examples with the table. So example 8, conditional probabilities with real-world data. Real-world data. This is actual data that was gathered in 2002. So mammography screening in 100,000 U.S. women ages 40 to 49. And it's a two-way table. It shows positive mammograms and negative mammograms out of those 100,000. It shows breast cancer and no breast cancer out of those 100,000 women. So we've classified our data 2 ways. Assuming that these numbers are representative of all U.S. women, find the probability that a woman in this age range, first of all, has a positive mammogram given that she does not have breast cancer. And the second part that we're going to do is what's the probability that she does not have breast cancer given that she has a positive mammogram. Okay, so these are conditional probabilities. Probability of A given B. So we're going to go to the next slide and talk about how to do these. And they'll have a table for us there as well. So part A. Probability of a positive mammogram giving that there is no cancer. Right? Look back at it. Positive mammogram given that she does not have cancer. So we're going to abbreviate our notation a little bit right here. Positive mammogram given that she has no cancer. So in that table, what we're going to look for is there are 99,200 women in the study that did not have breast cancer. So that's going to be the denominator of our fraction. So we're restricting our data or our sample space to this column right here. No breast cancer. What's the probability of a positive mammogram given that she does not have breast cancer? So that would be 6,944 out of the 99,200. That's the fraction. And then we'll grab our calculator and we'll do that division and come up with a decimal. So 6,944 divided by 99,200, that comes out to exactly 0.07. So 7% chance. Okay? So as it said, when we're dealing with conditional probabilities, we're restricting our sample space. Let's look at this last example, part B of example 8. So what we have, let's go back and look at it. We wanted the probability that she does not have breast cancer given that she has a positive mammogram. Okay, so probability of no breast cancer given a positive mammogram. So we're going to stay in this sample space right here. Positive mammogram, but I want to know what's the probability that she does not have breast cancer given that she had a positive mammogram. So total positive mammograms was 7,664. That calculation has already been done in the table. The probability of no breast cancer given that she had a positive mammogram, then the total sample space, 7,664, and no breast cancer in there, 6,944. So out of those that had a positive mammogram, 6,944 did not have breast cancer. So our probability is going to be that fraction. Let's grab our calculator and come up with a decimal answer for that. So 6,944 divided by 7,644, 0.906 when we round to 3 decimal places. So a little higher than 90%. And that is the end of our video.